I think we already 6 minutes over time. So we start today, this morning's second section. Okay, so we have two teams. One is Tsinghua University, physNTHU, and 成功 University, 彬彬小乌龟. Okay, so the first thing is that to decide who is the teammate, who is the teammate. So we take rock, close, scissors. Okay, you want to be, okay, Tsinghua University will be team A, then you team B. Okay, you need any preparation time? No? Okay. Please start your presentation for 10 minutes.
Okay, hello everyone. We are Team NTHU Physics, and I'm going to introduce problem 9, boiling a tube to you all, and hope you like it. The problem says, a sealed transparent tube is filled with a liquid and contains a small ball. The tube is inclined and its lower end is attached to a motor such that the tube transits a conical surface. And please investigate the motion of the ball as a function of relevant parameters. And we are going to solve this problem by 3 parts. First is, why does the ball move? And the second is, what parameters influence the motion of the ball? And third one, we want to find out how do the parameters affect the result? Okay, here is our outline. We were going to discuss this problem by 4 parts. The first part is preliminary observation. We have some experiment preliminary observation, and then we will introduce a theoretical model to try to figure out why and how does the ball move. And then we will have some experimental results to compare with our theoretical model and try to find the result of relevant parameters. And then we'll have a conclusion. Okay. First is our phenomenon. The phenomenon, we need to discuss the floater and sinker. And for floater, when the motor starts to rotate at a constant speed, then the ball will start to go inward to the motor as the video shows. And then if we change the angular velocity of the motor rotates, as you can see, the faster the motor rotates, the closer the ball will go inward to the motor. And for sinker, as you can see from the video, if we start to rotate, the sinker will start to go outward against the motor. And here is our theoretical model. And in this part, we try to figure out why and how does the ball move. At first, we need to discuss how does the water flow in the tube. So, as these 2 different video shows, you know that water will not move if the ball doesn't move. And then while the ball starts moving, liquid will cause drag. So the first part of our theoretical model, before the ball moves, if the ball is not moving, then the liquid will not move. So we don't have to introduce the drag force into this model. So this equation can be written as these 2 times. And if we let the gamma equals to the density of the ball, we can rewrite the equation as this. And since it's hard for us to determine the difference density between the ball and liquid to be 0. So if we want to find out where the net force to be 0, we have to focus on the last term, which is r times omega squared times cosine theta minus g times sine theta. So as you can see, if the last term to be negative for floater, the net force will be positive, which means the ball will start to go outward to its first situation. And on the other hand, if the last term should be positive, then net force will be negative. And for sinker, as you can see, if the last turn is positive, then the sinker will start to go outward to the motor. And if the last turn is negative, then the video. Okay. Yes, the video is not working, but it's not okay. So if the last turn it works. If the last turn to be negative, then the ball will start to go inward to the motor. And here is our second part of theoretical model. When the ball starts to move, we have to introduce drag force into our model. So by sigma F equal to m times A, we know that the first net force minus V times V squared minus the frictional force equal to m times n. And here, because the drag force sometimes is proportional to V and sometimes it is proportional to V squared, so we have to discuss whether it is proportional to. So we will discuss this later. Okay. And here we assume that when the ball is moving, it's doing a pure rolling. So the equation can be rewritten as this. And here is our experimental result. And this picture shows some experimental setup. And our method is we use magnet to fix the position of the ball. And wait until rotational speed is stable, we will pull the magnet. And then we can get the video in rotational coordinate system to analyze. And since our equation has a coefficient b, so we have to figure out how the figure of the coefficient b. So the method we use to determine coefficient b is terminal velocity. And when the ball starts moving at terminal velocity, the net force of the ball will be 0. So we can get coefficient b as this. And our result for floater, as you can see, the blue line, green line, and red lines shows 30 degree, 45 degree, 60 degree, respectively, to the theta the problem says. And the point on the plot is our experiment result. And it seems that our theoretical model is very similar to our experimental result. And for floater, we have to discuss whether the drag force is proportional to V or V squared. So for PV, we have the simulation as a green line, and for V squared, we have the simulation of the red line. And the black point is our experimental point. And it seems like it is clear that V squared is more similar to the experimental result. So we choose V squared as a proportional parameter as a function. Okay? And on the other hand, the velocity, the red line shows the V squared and the green line shows the V. And V squared is still similar to. And for sinker, the black line is our water sinker boundary, and the point is our experimental result. And we have to discuss V and V squared again. So the green line shows V and the red line shows V squared. And it is also clear that V squared is more similar to our theoretical model and experimental result. And okay, here is our conclusion. Our conclusion first is the sinker will either go to the top or go to the bottom. And the second is floater will sink and stay at a steady point. And third is we have the equilibrium point. Equilibrium point equals to g times tangent theta over angular velocity squared. And for floater, it has a stable equilibrium. And for sinker, it doesn't have a stable equilibrium. And the fourth is we can write the equation of motion of the ball like this. And we know that we need to introduce drag force when the ball starts moving, and the drag force is proportional to V squared. And the motion of the block can be simulated with a total force along the tube direction in a coordinate system with a tube, with a v-square dependence for the resistant force. And that's all. And here is our some reference, and that's all. Thank you so much.
Okay, the following up is the presentation for 10 minutes for彬彬小乌龟. Please use the microphone. Thank you. Or you can use this one. Just the cable is a little bit short.
Hello everyone. And the first time we'll apologize to everyone that we originally think we'll present by Chinese until we arrive here, but we'll still try our best to present by English. And this is, we are NCKU Physics. Our topic is Tesla web. And our topic is the Tesla web is this type of tube can let the fluid put in a positive side and a negative side of the fluid, and the outside of the velocity will always be different. And then we are talking about in any conditions and in any fluid, how does it work, and how different of the positive and negative types of the direction of the tube. And this is our outline. First we're talking about our theorem and our suppose. Then we'll use our design of the experience to talk about the function of Tesla web. And then we use our experience to get our final conclusion and data. First, we're talking about our theorem. And this is the most basic types of the Tesla web. As we can see this graph, this is a positive side of the Tesla web. We can see when the fluid put in the Tesla web, the fluid will go in a more short path of the direction of the side. And this time, this is a positive wave. When the fluid put in the Tesla web, the flow will be forced to separate in two lines, and then the two lines will collapse together, and we'll repeat this, or we'll repeat to separate and collapse, and then use this to decrease the velocity of the fluid. And at our experience, we'll design two types of different Tesla web, and this is the most basic way, and this is the Tesla web we designed by ourselves. And we use Rhino and Blender to draw the way of the Tesla web, and use a 3D printer to print it out. And this is our assumption. First, that we think in any fluid and in any time, the Tesla web will always work unless the Tesla web is collapsed itself. And second, the velocity of the fluids will always be different, and the positive wave will always faster than the positive wave. And the third is when the number of Tesla web increase, the difference of positive and negative wave will also be different more. The final is we are talking about the different type of Tesla web will have different effects of the positive side and negative side of the velocity. And then this is our experiment. First, by the Torricelli theorem, when a liquid was just be forced by gravitation, the velocity of fluid was just it is just according to the height of the liquid, but not by the area of the tube. And this is we can use the Torricelli theory to make our device. We fix the output of the water, and we can change the height of the water to change different speed of the water. And to change more velocity of the fluids, we use this button to change the area of the tube to change more velocity. And this is our result. First, we are talking about when the fluid velocity of fluid is slow and the number of Tesla valve is also little. What will happen? And this is our result. We can do these two graphs. This side of the graph is the velocity is smaller and smaller, and we can find out that when the velocity is smaller, the difference of the positive and negative wave of the Tesla valve will also be smaller. And this is the positive side of the Tesla valve. You can see its float is shortest path of the tube. And this is the negative wave. You can see the water will flow up all type of the tube, and the speed will be smaller. And this time we are talking about when we increase the number of the Tesla valve, what will happen and how different the positive and negative wave of the speed of the fluid. And this is our graph. And it's also when the graph is this way, the velocity is also smaller. And we can compare to the conclusion we get at the last experiment. We can find out that when the number of Tesla valve increase, the difference of positive speed and negative speed won't be different more but less. And finally, we are talking about when the Tesla valve was in the fluid of the fluid put in the Tesla valve was in very high pressure and high velocity. What will happen? And this is our result. We found out that when Tesla valve, when the water put in the Tesla valve, the final liquid speed and the positive wave of the speed and the negative wave will finally be almost different. And look at these two graphs. We can find out that at this conclusion, the Tesla valve, the function of Tesla valve was finally disappeared. And this is our final conclusion. When the speed of the fluid decrease, the difference of positive speed and negative speed will also be less different. And second is when the speed of the original fluid is very high and the pressure is very high, the function of the Tesla valve is totally disappeared. And finally, we find out that the number of the Tesla valve didn't cause the more difference of the positive and negative speed of the Tesla valve. And this is our presentation. Thank you.
Then both teams has 2 minutes to prepare for short questions. Time is up. So now, Team B, 彬彬小乌龟, please ask short questions to Tsinghua University for 2 minutes.
And our first question is you assume that your experience is you didn't sorry I'll talk by Chinese 就是你一开始没有考虑到 peer rolling 可是这个问题之后存在，那你要怎么？
Actually, we assume that motion of the ball is pure rolling. Yeah, we have to assume that because if it is not pure rolling, it's very hard for us to solve the equation. Yeah, it is hard to discuss. So we have to assume that if the ball is starts moving, then it's doing pure rolling.
And the second question is, sorry， 然后你们在讨论那个铁球跟保龄球之间的差别，可是你们那条公式，对，你们那里这个里面根本就没有跟铁球跟保龄球有关的参数，那你要怎么样去讨论？
Actually, the gamma is the density of the ball. Yeah, we let the gamma here. We let the gamma as the density of the ball. So if we change the ball we use, then the gamma will change.
Okay. Now, time for Tsinghua University to ask question to 彬彬小乌龟.
Okay. First, please show your data. Okay. In your y-axis, you mentioned that the speed is g over s. What's the definition of your speed?
你可以用中文，
Please.
你要用中文或英文回答都可以。
Well, I'll talk about a solution. 我之后再回答。先。
Okay. So how do you measure the v? Your speed v? How do you measure it? Okay.
他现在需要一些短答案，他才知道后面要跟你讨论说要怎么继续，所以你可以给他一个短答案。
好，第一个问题是我们是借由出来的水量，因为那个水量是固定的，我们所以有一个固定的水，我们是它跑出一样就100克，就是100克或200克的水量，然后当然我们有同时按码表计时它会跑多久，这样。
Okay. Then how do you measure the v? How do you measure it?
对，我刚讲的。
Okay.
They use the mass of the fluid.
Okay, I got it. You mentioned that you assume the velocity is linear relation. Did you try other relation, like square proportional to v square or proportional to v? Did you try?
因为它其实我们探讨这个流体是一个算是极度不稳定的关系，所以我们很难去用，因为它本身流速就是有很不固定的东西，它里面的流动有时候也会某些摩擦或其他的东西，让它导致它有时候会偶尔会发生失衡的状况，所以我们只能以大约线性或者是甚至是正相关的讨论。
Thank you.
Okay. Okay. The discussion will be divided into 2 parts. First 4 minutes will be focused on the presentation of Team A, and the second part focus on the presentation of Team B. So we start the discussion now, please. You can speak in Chinese, and you can choose to answer in Chinese or in English. That's okay.
好，那我要问你们是拿那个保龄球跟铁球当便吗？可是它本身的那个浮体特性就不一样，一个是浮体，一个是沉体，那你们要怎么去？你们要怎么去说啊？你们做出来的结果一定不是因为这样的浮体特性不同影响
？Actually, we 我们分成两种情况讨论。第一种情况是，我们分成两种情况讨论。第一种情况是浮体，第二种情况是沉体。那两个情况本身就会不一样，所以我们结论会有提到说，对浮体而言，它本身会有一个 equilibrium point， 可是对沉体而言，它会直接 go outward， 它会直接到最远，就是离那个马达到最贴在管壁，它直接撞出去。就是这个 video 可以。这个是，就是我们分别对沉体跟浮体讨论，这个是沉体的部分。沉体的话，我们可以确定前面那一项一定是正的，但是后面那一项就是我们要考虑的变点。如果今天后面那一项是大于0的话，它就会往外冲；如果后面那一项是小于0，你就可以看到右边那一项是往内。那对浮体而言，我们就可以知道，它会有一个平衡点。OK， 这就是我们讨论的部分。
然后你们就是对于沉体的结果就只是撞到底端，对不对？
是，我们可以利用这个方程式去找出它的那个平衡点在哪里。就是理论上来说，如果它在这个点上，这个沉体也会在一个固定点。但是实际上我们很难去控制找出。我们其实有那个就是我们可以知道。从这个理论，我们可以知道，就是当它后面这项路大于0，它会往外走这样。那如果就是我们可以从这条线去预测，理论上来讲，我转速多少的时候，它应该停在哪里？这是我们实验结果。
那你们能确定它撞到就是它撞到底部的时候是已经是平衡的状态吗？可是你们就只是用你们自己的预测，是觉得它可能会。到什么程度？
撞到底部吗？我们不称撞到底部叫平衡状态。我们所谓撞到平衡状态是指它会停在固定的一个点。所以对我们在沉体部分，我们很难找出它，就是很难做出它刚好停的那个点，因为我们很难去控制那个角速度。但是对浮体而言，我们是可以控制的。所以在浮体的时候，我们可以确定它影片就停在，你可以看这个影片。对浮体而言。它在转的时候，它的确是停在这3个点，所以浮体我们是可以控制它有一个平衡点，但是对沉体而言，自己是很难控制，所以它会有一个往外走，所以我们就最后就提到说，我们对沉体的定义叫不稳定平衡，对，就是所谓不稳定平衡，就是它差一点它就会跑掉，稳定平衡就是我可以去看到它就是在那个点。
所以你们就只能做到它就只能到那里，所以你们就是没办法找出它平衡点在哪里。所以从应用上来说，它是不稳定的。
平衡的点在哪里？我们有找出它的运动方程式啊，我们有找出它的 VT 图。但我不太懂你的所谓平衡点在哪里，因为我们管子就这么长，它就是贴在那里嘛，我们没办法说再改变那个长度，对，所以它就这么长，所以我们最多只能找出那个 VT 图。
Okay, I think time is up. So, it's not up.
OK， 那个你可以再秀你们 data 一次吗 ？Sorry。你的 data OK， 你的那个 data 里面，你说你可以再解释一下你们的图表吗？再解释一次。
对，因为我们是想说用那个就是流速，因为我是图表越往右，它速度越小。就是成一定的关系，因为我们是用水的高度，因为我没有算实际它到底是多少，可是我们知道它是以一定的比例慢慢下降。
可是你这一个点它并不是，而且是有点往上凹的感觉。
对，因为像蓝色的点跟橘色的点，它是就是它的那个截面积有变， 对，可是它前面的截面积比后面还要小，所以因为我们是水高度的关系，我没办法一次做出很多个不同速度的变异，所以只能用这种方式。可是因为我们就算没有这样做的话，本身流体的特性就很不稳定。例如说，你同样水位的高度，你可能因为管子暗，它里面水可能里面不只有水，就是可能其他杂质可能都会影响它的流动，所以它的流体是一个非常不稳定的状态。所以我们只能大概找出大约的关系。
那这样子，你们那个越往右边是什么意思？那个 times 是什么意思？
就是我们就是速度，就是我们只能这样标记，就速度1、速度2、速度3、速度4，然后越往后面速度越小。
越往后面是什么意思？是指时间吗？
就图表的有明显图表的横轴不是时间，
那它是什么？
是次数。第一次测的时候在哪，第二次测在哪一个点？
那它下面标的那个是指就是第2次、第4次、第8次？
对，它不是时间。
OK。好，那你们的结论有提到，或者是可以掐结论。你们结论提到了，the more valves have the difference of velocity will be more insignificant。所以你们意思是说，你们的那个 valve 如果越少，越多的话，它们减速情况就会越来越小。
对，就是其中一个我们就是结论跟我们的假设违背理论，就是因为我们从第一个结论可以知道，当我们原本流体的流速越慢的时候，它影响会越不明显。然后当我们特斯拉法接越多，在它被流体被特斯拉法影响之前，它速度减慢的效果就远大于特斯拉法本身造成的效果。所以说，接越多反而会让越快，就是它本身就先被它本身速度减慢的效应抵消掉了。
所以假设现在有一个特斯拉法，然后原本速度是1，那它可能过去速度是0.5。那现在假如我接了3个特斯拉法，我1过去，它会比0.5大概是比0.5小，它会比0.5小。但是你可以大概知道它是几倍吗？
这个它就是像我们右边的图表是只有接1个，左边是只接3个。像看3个，你看它的那个纵轴，它就是在范围是在1跟3之间嘛，就是它其实大概也算是一个，我们只能说它是负相关，因为它这个变异真的太多了。因为你如果同时，因为我们都是在同样的速度之下做这件事情，你如果要让它有差别的话，你只能改变它的速度，这样。
那所以你们这实验是大概做几次？这个图是平均下来吗？还是说你们就做1次，然后？
对，是平均下来。
平均下来的话，那你们的那个 error bar 大概是多少范围？就是你们的那个实验误差，不可能说平均下来就是这个点，然后你就是怎么测就是这个点上面，所以它大概范围是。
因为它大概范围其实因为它流体的特性，就是因为我们用的是自来水，然后我们可能不知道有可能是管壁里面有东西还是怎样的影响，所以我每次测就是一直跳。我们是从中里面找出感觉里面比较相对稳定的值，就是确定它可能没有在那个时间没有被影响的状况之下才，这些数据是这样来的。
那你们怎么确定什么叫没有被影响
So yes, the time is up. So the last question. Prepare for concluding remarks. Team B, please make your concluding remark and the conclusion for this kind of discussion. 还有那个 OK.
好 ，OK， 我们结论是你们的数学理论的假设跟实验非常契合，然后理论本身也非常完备。可是我觉得你们的问题是你们只讨论单一的层级跟单一的浮体，搞不好对你们没有讨论在不同的层级或不同浮体之下会有什么结果。这样，然后我们自己的问题是我们没办法很有效的控制流速不稳定性这个问题。可是我们有试着在尽量固定同样的背景因素之下去探讨这个实验。就这样，谢谢。
Okay, thank you. Now it's the time for Team A to make your conclusion.
我 我们的结论是，就是我们可以找出一个方程式长成这个样子。然后对浮体而言呢，我们可以确定它的平衡点在哪里，而且当当后面这一项如果是小于0的话，那本身因为密度差是小于0，所以它就会是正的。那正的话，它就会开始往外面移动。然后如果它今天力是正向的话，那它就会往外面移动。然后如果力是负向，它就会往里面移动。然后对成体而言的话，密度差大于0，所以如果今天你的后面这一项本身如果是对成体而言，它有可能会到底部，或者是到到马达底部，或者是它会到那个管的底部。所以如果今天你的力是正的话，它就会到管的底部；如果力是负的话，它就会到马达的底部。然后 boundary 我们可以预测它的 r 就会是长成这个关系。所以我们只要去改变它西塔跟它的 omega， 我们就可以知道它的点在哪里。但是对，然后这是我们的实验数据，我们其实找出来了，就是 r 跟 omega 的图，就是我们在哪个 omega， 我可以确定它停在哪里，对同一个角度而言，所以就有3张图这样子。然后这个浮体我们也找出了它的 xt 图，还有 vt 图，然后也就是实验跟理论其实非常的契合，这样子。然后成体的部分呢，我们一样找出它的 xt 图跟 vt 图，那这样我们其实就可以知道它在哪个时间点是停在哪个位置，这样子。如果我们控制它的 omega 的话，那对成体而言，刚刚讲过，成体是一个不稳定平衡，意思就是说，它如果在这条线的左边的话，它就会往那个底部，就是朝向马达；如果它是在右边的话，它就会往管子的底部。对，然后我觉得你们的问题就是你们的图太小，然后而且就是解释的时候没有着重在就是解释多一点，而且你们实验重复性感觉也看不出来你们实验重复性到底是几次。还有就是它那个趋向其实跟你们假设是不符的，还有那个结论其实是有点怪。就是理论上，如果 VAV 更越多的话，它应该我在数据上面显示看过 ，VAV 只要增加2倍，它的流速差就会差到100倍。对，这个可能是要再确认一下。
Okay, thank you. Question can be in Chinese or in English.
我想你解释一下那图上的150度跟180度是。
就是那我们要调节面接收这个，然后可是我如果没有这个，我们没有这个词的话，我不知道我到底转了多少人。对，然后我们是以这样标定，就是它全部关起来的时候是20度，然后它慢慢转到150度，它会解密机会变大，然后180度又更大。然后关于大多少，我们是没办法确定，可是我们知道它已经很大。
Okay. Any further question?
Just in my opinion, okay, you cannot call it stable and unstable. Because you cannot call it because suppose in the system, suppose we call it unstable means it's just a fluctuation. But now it's the ball, okay, resides with the top of the cube. So it's your design problem, not a system problem. Okay, so you cannot call it unstable. Okay, you know what I mean. You know my understanding. Okay, thank you.
我想这是个简单的 comment， 因为我觉得你的东西感觉上没有 touch 到这个特斯拉 VAV 真正最重要的 point， 因为其实这种 VAV 可以看得到它的 design 是没有什么可动的部分。那这种通常会装的地方都是那种装了一个可动部分之后，那个可动部分常常就会坏掉。例如说你放在那个超高压的蒸汽环境，那这种法就很适合你放进去之后，你只要设计得好，前面跟后面出来是完全可预期的。但是它所谓的可预期可能不是个 steady flow。所以我想你在分析的时候，你希望它是个 steady flow， 可能这个问题就有点就是有点怪怪的，因为它可能就是随时间在 fluctuate。那你可能如果你看到这个现象，通常应该讲，我们做实验通常看到一个随时间在 fluctuate， 我们第一个关心的是它有没有周期。对，因为一有周期之后，你就把它整个周期的事情平均起来，就有很漂亮的平均值。通常我们会这样处理。然后那 既然你的现象已经看到不周期了，所以你下一个会 concern 的事情就会是，你的流体是不是还是层流？对，大概就会开始在担心它是不是还是层流。所以因为我看到你在弄东西的时候有弄那个好像染料，所以你其实可以那个染料弄的量让它变成一条线，那看它有没有最后整个都 mix 在一起。那有的话就是你就确定它里面基本上是一个混的，那不然的话你就可以继续是在层流的情况。那层流的情况会出现流速忽快忽慢，这就表示里面的现象很诡异。那你们的那个是透明的，你其实可以看着它从第一段、第二段、第三段，到底中间发生了什么事情，可能也许还没办法完全用定量的数字来描述，但是至少你可以讲一些故事出来。这是我的看法。那这个for the tube, I think that you do miss a lot of points between the difference between theory and observation, because you see that when you add the friction point or friction force or some retarding force into your model, your data actually cannot fit to the theoretical curve. They deviate pretty much. Yeah, so I think that's the point for this kind of study should overcome. Yeah, that means the model you use actually doesn't work very well. So I think that's the point. That's the very big point. Yeah, that's the previous graph. Yeah. Okay. Since then, we give the score for the two teams. We start from Team A, Tsinghua University. So the points are 7, 8, and 8. And for the Team B, points goes to 6, 7, and 7. Okay, thank you. Now I would like to close this section and thank you both team. Yeah, 我觉得你们非常勇敢，这个
准备中文表现不错。